Good day. Once again, welcome to another discussion. This time, we are going to talk about the basics of Rankine-Regenerative cycle. So we can discuss it. We are going to have here the schematic diagram of the Rankine-Regenerative cycle. We know already our Rankine cycle that is composed of the boiler, turbine, condenser, and a pump here, so that the idea is to come up with a cycle that generates work. Here, the regeneration actually is the another way of improving the efficiency of the Rankine cycle. So let us connect our boiler to our turbine, and this entrance point here is called the throttle point. We normally call it point 1, and we have here the steam expanding inside the turbine. It comes out at this point towards the condenser, but we notice here that we have open heaters included in our cycle, so that the purpose of these open heaters is to provide gradual reheating of the saturated liquid that comes out from the condenser towards our boiler, so that instead of the usual expansion of our steam from 1 to this point here, we are going to make extractions, say at this point here. I would like to call it point 2. So there is a partial expansion of steam from 1 to 2, and that part of that steam is taken out and conveyed to open heater 1. And the steam continues to expand. Again, we have another extraction point here, call it point 3, that directs the steam to open heater 2. Steam continues to expand, and another point here, call it point 4, which takes again steam to open heater 3. In this case here, in this example, we have 3 open heaters in effect to this cycle. So we have from 1 to point 2, and we have here extraction, and another extraction at point 3, and another extraction at point 4. Now finally, steam comes out from our turbine at point 5. It then enters into your condenser, and there is constant pressure heat rejection process that takes place here, so that steam becomes saturated liquid, and this point is, we call it point 6, and our liquid is then pumped to open heater 3. You have a pump here, so that this allows this low pressure liquid to enter this open heater. This one would have a higher pressure compared to this liquid here, right, as it comes out from the condenser. Okay, so we connect this here. I would like to call this point after this pump but before this open heater as 6B. The masses taken out at points 2, 3, and 4 will be named M1, M2, and M3 respectively. So at this point here, M3 would mix with that mass coming out from this pump here at 6B. Mixes with M3 and comes out at this point here. This point, let's just call this 1,7. And we pump it to open heater 2. This point here, let's call this 1,7B. And another point here, exit point of open heater 2, we call it 8. And we have a pump here, 8B. And this saturated liquid, all of them would go back to the boiler, and they would be pumped by this main feed water pump back to the boiler here. So here on the boiler we have the heat added to the boiler. That's the QB, which we are going to solve to calculate later. The work provided by our turbine, call it WT. The amount of heat that is rejected to the environment, call it QR. And the pump works here, since we have several pumps. Pump work 1, pump work 2, pump work 3, and pump work 4. We would take the sum of these pump works to be able to determine the total pump work required by this system here that we have. On the TS diagram. So from the schematic diagram here on the expansion, we would like to translate this into the TS diagram so that we can see, we can determine the properties. So this is starting point at the throttle point, point 1. It partially expands to 2. And some mass M1 is taken out here. That's our M1, goes here. And at point 3, M2 is taken out. And at point 4, M3 is taken out, such that what continues to go to our condenser actually is whatever mass we have here that enters the turbine less M1, M2, and M3. To simplify this one, let us just agree that we have a basis, a unit basis for purposes of calculation. Suppose we have here a kilogram of steam that enters the throttle point. So that if M1, M2, M3 are taken out, clearly what continues to what goes to the condenser would be just 1 minus M1 minus M2 minus M3. So to calculate for turbine work, we would like to take note that on this expansion here from 2 to 3, there is already an M1 that is taken out, so that it's just 1 minus M1 that takes effect, that does the work here from 2 to 3. And further, from 3 to 4, there will be just 1 minus M1 minus M2 of steam that provides the work. here. And on 4 to 5, it's just 1 minus m1 minus m2 minus m3, like what we have here, that continues to enter the condenser, comes out at 0.6, which is reflected here in our schematic diagram here. So the throttle here in this condition here on our TS diagram, and we would like to recall that the expansion actually is isentropic. So we have here a vertical line connecting points 1 to 5, here 1 to 5 as an ideal case that it is an isentropic expansion. Now at point 6, where we have the pumps already on this side here, and these are ideally saturated liquid conditions here, 100% of them. So this one is 0.7, this one is 0.8, and this one is 0.9. By the way, we have that here. So pumps here, pumps and the open heaters. So by the way, after 8B here, the point before the main pump is number 9 in this drawing, and the point after the pump as it enters the boiler will be called point 10. So we have that here. So 0.6, and we have a pump here. So we have this pumping, and that is 6B, and this mixes with the extracted steam at 4, and the condition is ideally considered to be saturated liquid, and that again is pumped to this condition here, call it 7B, and it mixes with diffraction bled steam from 3, and again another ideal condition that it is saturated liquid, and it is pumped to 8B and mixes at open heater number 1 here, mixes with what comes out from 2, so that is at 0.9, and finally a main feed pump pumps this to 0.10, so it enters the boiler, and you have here your cycle. So the cycle is from 1 to 10, and it continues. So we are going to analyze our regenerative cycle based on our TS diagram here, and also with our schematic diagram. By the way, the points here, these points here are governed by the steam properties, and the enthalpies that we need in order to calculate for the required quantities like the turbine work, the heat rejected, heat added to the boiler, pump works, are all taken from the steam tables, and we know how to determine those properties already. Fraction bled steam. These fractions actually are those M1, M2, M3 that we take out from the turbine. From the schematic diagram here, we can see that is M1, M2, and M3. These are taken out. Now, how do we calculate them? Because this fraction blade steam would affect the performance of our steam turbine, and also it affects the amount of heat that we removed from the steam. Since these masses here are not included in the heat rejection somewhere here in our condenser. So how do we determine this M1, M2, and M3? Now, for M1 is that amount that enters open heater 1 here, and this one is connected to point 2. Now our steam turbine goes to open heater 1, so we can call it 2. This is from 2, and M1 enters here, and this one is 0.8B, and this one is 0.9. So we can check it out from our schematic diagram here. That's 0.8B, open heater 1, and 0.9 here. So it's from here that we determine the M1 by mass and energy balances. Okay, so what enters here would be 1 minus M1, and this 1 minus M1 amount of saturated liquid comes in contact, mixes with M1 here, that fraction that is being extracted at point 2, and they would mix so that this will just be the 1 kilogram basis that we had. We have agreed on this for purposes of calculation. Later on, we're just going to multiply this to whatever amount that we have that actually takes part in the cycle. Okay, so we do here the energy balance. So that what enters the open heater 1 is the energy balance at open heater 1. So we have here that M1 times H2, that's the enthalpy, assuming that an ideal case, that's the enthalpy of the steam at point 2 as it is being extracted, multiplied with M1 plus the 1 minus M1 times H8B will be equal to this one, this comes out here, will be equal to 1 times H9. So we would like to simplify this. And clearly from here, you can collect M1 and you have H2 minus H8B equals to H9 minus H8B. So let's take it from there. From here, let's transfer that here. So we have M1 H2 minus H8B equals to H9 minus H8B. So this actually is the result of simplifying these things here, so that M1 is just equal to H9 minus H8B all over H2 minus H8B. Yeah, so we have here. But on the next masses that we are going to determine, we will encounter that this will become complicated, in the sense that there will be several terms to be simplified. So from here, we are going to come up with a pattern so that we will be able to come up with the equation right away by just looking into the drawing. So there is a trick for that, a clue that we can use. So therefore, calculating the rest of the masses M2 and M3 will become somewhat easy. So let us consider this as our open heater. We have here the mass that comes from the side here. Okay, so in the case of open heater 1, it was called M1, and we have here 1 minus M1, and we have here H8B and 9 here, and that's M1 plus 1 minus M1 gives us 1, with this 1 kilogram basis. So we would like to agree on here on some things. This would be H9 and this would be your H2. And take note that this H9 minus H8B, H9 minus H8B is actually the energy that is actually absorbed by our saturated liquid. So that you think of this one as what is being absorbed. While the other one, so what we have here, M1 equals to these things. H2, this one here, that steam from the extraction point, minus H8B. This difference here actually can be thought of as the available energy that can be transferred to your saturated liquid. But in this case here, it's just H9. It's not really the H2. H9 is very less compared to H2. So this one is available. Just remember these words here. This one, the numerator is the absorbed energy divided by what is available. so that this mass here that is unknown is simply equal to what comes out here, 1 times what is being absorbed divided by what is available. So that if we are going to solve for M3, I mean M2, and from here, from our schematic diagram, we're going to solve for M2, so that the points involved here will be 7, B, and 8. So we have open heater 2, and we are going to transfer that here, solving for M2. So that's open heater number 2, and we have here M2 going to open heater 2. In this case here, we have this one is connected to point 3, which we have H3, and 7B here, and 8. So if we do the energy balance here, cause energy out, can always do this one, but sometimes we need to save time, so that based on what we have developed here, we know that what enters here will be 1 minus M1 minus M2, so that when it mixes with M2 here, what comes out at this point would be just 1 minus M1. We have solved already M1 previously, so that 1 minus M1 is already available. So if we base our solutions to that suggested that what we have developed here, we have a shortcut. We can come with a shortcut, so that M2 is simply equal to what comes out here. Never mind this one. You do not look at this. So it's just, what is this amount here? Call it M2 is equal to what enters here, 1 minus M1, which we know because we have calculated M1, times what is being absorbed, H8, minus H7B, divided by what is available. In this case, that is H3 minus H7B. So we have here our equation that helps us solve for M2, and without having to waste our time in simplifying terms in this equation here. So just remember this. Just remember this one every time we deal with the fraction bled steam on the open heaters. And finally, let us further apply our shortcut in solving for M3. Let's look at our schematic diagram here. It's open heater 3 that involves M3, so that points 6B and 7 are involved. So we're going to transfer this. We have here our open heater number 3, M3 here enters open heater 3. This is connected to point 4, therefore we have here H4, 6B, and 7. So from this schematic diagram, we know that what enters here will be 1 minus M1 minus M2 minus M3. What comes out here is 1 minus m1 minus m2. So again, we apply our shortcut. M3 is simply equal to what comes out here. This point is 1 minus m1 minus m2 times what is being absorbed, that is H7 minus H6b, divided by what is available, that's H4 minus H6b, so that we are able to calculate right away for the M3 without again having to waste our time in simplifying terms on the conservation principle, energy in equals energy out. So this practically allows us to solve for diffraction bled steam. And so far, we have covered already the basic things about the Rankine-Regenerative cycle. So in the next clip that we're going to develop, we're going to take up an illustrative problem regarding regenerative cycle. So for now, this will just be all. Thank you for watching.